Okay. Hi, I am Borja, and today I'm going to be presenting this paper that we released a while ago and that will be published very soon. And it is called Automatic Detection of Nuclear Spins at Arbitrary Magnetic Fields via Signal2Image AI model. Here you have the reference of the archive for now. And well, what is the main objective of this work? It was to detect the nuclear spins, the coupling constants between the nuclear spins surrounding the MV center and the sensor. And these spins are from carbon-13 nuclei that are in the diamond lattice naturally. And why did we choose to use a deep learning model? Because first of all, these models offer a fast characterization once they are trained, and they are also known to be robust to different noises in the input signals, and this is very useful, for example, in our case that we want to work with real experimental data. And in our particular case, we built a model that is not dependent on any feature or any characteristic of the input signal, such as resonance peaks, etc. And this makes it very suitable for various magnetic fields, for example, high and low magnetic field. And another characteristic of the model is that you don't have to previously know how many nuclei there are in your sample to make it work. This is not a condition.
What does fast mean?
Fast. Well, this fast here I have not explained in detail, but is in comparison to classical algorithms where you have to do simulations, Fourier transforms, and analytical calculations. In this case, you have like a compact model, a black box, which you give these input signals, and in milliseconds, like very fast, you obtain these coupling constants, these parameters, without any calculations, any intervention of the human being. Or
Fine, but to obtain the input signal, how much time
okay,
should be
that is the input signals that we have worked with in this case require like about 3-4 hours of taking information in your experimental setup, but this is one thing that we have been working on in improving this time, doing less measurements, and when I will explain later a bit in detail this aspect, but yes, it's like about 3-4 hours.
3-4 hours?
In the example that we explained in the paper.
Okay, so the input signal that someone has to provide you takes approximately hours.
Takes hours.
And then once they give you this info,
but then it will be like automatic to obtain the result. So, well, I will discuss this later. So here is the system that we are working with, which is, of course, the diamond lattice, where we have this MV center, and in diamond, naturally, we can see carbon-13 nuclei in 1.1% of density. So these nuclei have a spin due to having this extra neutron or whatever, and we can detect them using MV sensors. So here is the Hamiltonian that represents this system after applying a pulse sequence similar to what we see right here, which is a simple sequence composed of n pi pulses. In this case, we obtain a modulation function, this ft, that changes between 1 and -1 every time a pi pulse is applied. And the objective is to obtain this A, which are the coupling constants between the sensor and the spins. And we considered no interaction between the nuclei, and this makes it possible to treat them as independent and to represent them just using 2 axes, the z axis and the perpendicular axis, instead of 3. So, well, as I said in the beginning, we have worked at high magnetic field and low magnetic field, and this is just an example of these 2 values of the external. Yes?
here later and explain it later. But the carbon 30 that you, because this is you're explaining now the stuff that you measure with the integration frequency, but you are speaking about the carbon 30. But what is the effect of 30?
Well, the idea of measuring these coupling constants is just to characterize the system composed of the sensor and the carbons. And this would be useful, for example, because all of these spins are qubits, so to treat them as a, I don't know, like in quantum information, as a platform where you have many qubits characterized. And it's just a characterization method to use them in other applications or.
The carbon 30 is like very important in that platform.
As a qubit, yes. Both the sensor and the carbon 13 spins.
So the carbon 30 is you want big coupling constant with the carbon 30.
What?
That you want coupling constant with the carbon 30.
Yes.
You want a big coupling to use it later.
Yes. Well, there are other applications, but it's one of them. Like to characterize the system is like the first step, and then you can do many things.
The idea is that use as quantum elements. So you produce, you have a chip, and those of these fastly characterized.
Yes.
I think it's more in that direction.
That's the idea. Well, as you can see here in these plots, at high magnetic field there are these resonance peaks, but at low magnetic field the spectrum becomes quite messier. So techniques that rely on these resonance peaks, of course, in this case, do not work. So this is why we wanted to build like a model that took this into account, all these scenarios. And well, in these examples, we can see a signal obtained from a sequence of 32 pulses. And here what you do is to apply this pulse sequence, measure the MV, you do these measurements n times, and you obtain one data point. And then you change this tau, which is half the interpulse delay, the time between the pulses, and you obtain these plots, these signals. So in total, you have the number of points times the number of measurements for each point. This is the total number of measurements that you have to do in your experimental setup. Okay, and of course the previous plot was an ideal plot simulated with there is an analytical expression, and then what we did to adjust these plots to real conditions was to add the coherence, first of all multiplying by an exponential decay with T2 equal to 200 microseconds, and then we simulated a number of measurements, in this case 1000 measurements for each data point, and then calculated the average. And in this way we obtain a signal with noise and the coherence, which are the two important factors in an experimental setup. So now that I have presented the system, I want to present the model that we built to deal with this problem, which is called the SALI model. And SALI comes from Signal2Image, artificial intelligence model, or it may come from the name of my village, which is Salinas de Buradón, SALI, the one that we see right here. So you can decide whichever you prefer. I prefer the second one, okay. Now, this is the schematic representation of the model, which at first it may seem that there are a lot of things, but in fact there are two main things, which are this neural network module and then the image post-processing. The first part takes the two input signals, process them into an output image, and then of course if we have an image we have to process it in some way to obtain finally the number of nuclei and the coupling constants that we want. Okay, first I'm going to explain roughly how this neural network works. I'm not going into many detail, but it's formed of 3 blocks, which is the one-dimensional convolutional block, the fully connected block, and the two-dimensional convolutional block. So this first block takes the input signals and kind of extracts information about the patterns, the ups and downs in these signals, and then gives this information to this intermediate block, which kind of connects the 2 convolutional blocks. And in this way, we can also adjust the shape of the output image that we want in the end using this block. So, and finally, we can process this image in the 2-dimensional block until we obtain the output, which I don't know if you can see very clearly here, but the output is just a black image with points, little points, and each of these points represents a nucleus. That's it, more or less. Okay, so this is kind of...
In the last part, you paint, right?
Yes.
In this black, let's say this black, whatever. So it's something that says yes or no, depending on the, no?
Yes, it's...
So depending, so it's like it's say that it's scanning all the parameters, and then they say yes, yes, no, right? And if yes, they go.
Yes, it is a yes or no, but it also has some kind of details. For example, yes or no, but with what, I mean, if the point is stronger, it means, for example, that the network has more confidence in this detection than in other detections. So you can play also with this confidence of detecting one or another. Maybe in other plots you will see better how this shows, because here you cannot see very well.
For example, to have this kind of circles, no? I mean, this is the sum of some number of pixels, or
Yes.
one circle is 1 pixel.
No, it's like representing a Gaussian function. It's areas of 5 times 5 pixels. These are numbers that you can adjust. It's like if you draw a point, for example, in an iPad or whatever, and you go like this, what you see right there is more or less similar to what this is. So you can make bigger points, smaller points.
So you could have a single white pixel, which is maybe a
Yes, that is one thing that we tried in the beginning, but if you only represent it with 1 pixel, it's easier for the network to forget about it, to mess a little bit. So more pixels give it like more weight in the image, and well, this is what has worked in the end. So yes, but it's like, in fact, I tried drawing a point in my tablet and it's the same. So that's it. And well, these are some technical stuff, which is that we train the network for both high and low magnetic fields using 3.6 million samples, and each one of the samples contains a random number of nuclei between 1 and 10 with random parameters of AZ and A perpendicular in these ranges that we see right here. So in the end, each sample contains a set of AZ and A perpendicular, this set. And as I said, these nuclei are represented in the output as points, and that's it. And you simulate the input signals with these parameters, of course. So now, these signals contain each one of them 1,000 points. And I haven't mentioned, but here you can see 2 different signals of different duration. This was in order to detect strongly and weakly coupled spins. So you have, for example, this has longer duration than this. This makes it quite easier for the detection of a wider range of parameters.
No, I was indeed for there are parts in which you can simply the network is learning nothing. Right? This part where everything is sealed, right, in the middle of the load. So that's
Yes.
something we were discussing experiments data, so there are many.
Yes, that is one thing that we discussed, which is how much information you can extract from a signal. Because Even if you have maybe the best model to extract information, the information has to be there. So this is like we have not measured the information in this signal, have not analyzed this, but maybe it's something to do in the future.
Pre-processing of the signal.
Yes, or to optimize maybe the sequence, the number of pulses, the measurements. Yes, that is one thing that I will mention in the end, but well, spoiler. Okay, so now the second part is the post-processing module. Here the idea is just to extract these points that I will call clusters of pixels, but are points. And we have to count them, the number of points, and then the exact value of the parameters corresponds to the centroid of these clusters of these points. So here we can see the representation of the 4 stages, more or less, of the post-processing, and I will go one by one to explain. Okay, first of all, here is what we have talked before, which is the image that we give to the neural network. And here we can see these points that are perfect Gaussian functions represented in a 5 times 5 square. So that is what the network should replicate perfectly in the ideal case. In the real world, this is not perfect, but of course we have more or less, they are not Gaussian functions now, but they are like clusters of pixels. So here you can see what I said before. For example, this pixel has more weight than this one, for example. So this more or less shows the confidence with which the network predicts this nuclei. So now that we have this, we have to process this image. And how can we do this? Well, first of all, again, technical stuff, but first of all we apply erosion and dilation techniques, which are simply to smooth a little bit the image, and then we applied a threshold to get rid of the noise of the, maybe there are small values that you want to get rid of, so this is the second part. And then finally you connect the pixels that are adjacent to create these clusters, these predicted nuclei, and in this way we can count them to obtain n, and then calculate the centroid of each one of them to obtain a set and a perpendicular. This is more or less how it's done. And we obtain this picture with the white boxes enclosing each of the nuclei. And then the final part is to evaluate. So we plot in this, you cannot see very well here, but well, we plot in the same image the true nuclei, which are these ones, and we compare. If there is an overlap between the two boxes, it will be considered a detected nucleus. And this leads me to the final part, which is how we quantify these results, how we see if this is good, if this is not. So, well, we did not decide a single metric that took into account all the aspects of the model, so we chose 4 metrics distinct. So these are the first 2 metrics that are precision and recall, and this is based on purely the number of nuclei detected. So we consider a true positive as a detected nucleus, then we consider a false positive as a detected nucleus that should not be there because there is not in the original signal, and a false negative, a non-detected nucleus. So in this way we can define how good the detection is in comparison to the false positives in this case, and in comparison to the false negatives in this other case, precision and recall. And we can plot them for the different numbers of nuclei in each sample. Here all these plots are for the high magnetic field scenario, but well, it was just an example. Then what else we can do? In the case that we detect a nucleus, the true positives, we can calculate the coupling constants and compare them to the true ones, the original ones. And in this way, we can obtain the mean absolute error, MAE, between these values. In general, at high magnetic field, the AZ component is more accurately detected than the A perpendicular. This is quite common due to the nature of the signal, etc. And finally, this is what I mentioned before about the information that the signal itself contains that you can extract from it. So to compare this, what we did was to take the original signal, which is the one in black, like in the back that you see here, and compare it to the signal reconstructed with the predicted nuclei by the model, which is the blue and the orange for the cases of the two different input signals. Well, this is the mean absolute error for these signals, and in this way we thought that more or less the analysis was complete using these four metrics, and you can get an idea of how it works. And now, well, this is kind of a conclusion, perspectives. So what we did recently was to test this model with noisier input signals to see if it's robust to shot noise. And well, we added this in the appendix of the paper. And in general, we saw that the results were favorable. So this means that we could maybe decrease the number of measurements needed for obtaining the signal, and decrease also the experimental time, which is one idea. And then, well, next steps for this are, first of all, to try this in a real experimental setup and see if it works. I hope so. And then to use it directly in an experiment. And then another idea was to include this just as a tool within another model. For example, we see this model right here from this paper, and this is an interactive model with the experiment that the objective is to optimize the experimental time, balancing it with the precision that you want to obtain. And well, this is one idea that people in Edinburgh proposed me, which is to substitute this part with the model that we designed. And I should probably work on this when I go there during my stay. And that was all, I think. Thanks a lot for your attention.
The fact that the AZ is better predicted with higher fields, and this is because the sequence, the nature of the sequence.
I can't remember exactly, but one component of them is proportional to the width of the peaks, and the other one is proportional to the position and the other parameters.
Because when you have just one nucleus and you do the sweeping in tab, you have that the population transfer is centered in the Siemann frequency of the nucleus plus like A set or A set or something like that.
I don't know.
But
I remember that there is an explicit analysis on this, on the relation between the peaks and your parameters, but I think that's the reason that the origin of this. I suppose that the perpendicular component is more sensitive to small perturbations in the peaks, in the width or in the position than the other one. That's why you cannot detect it as precisely as the other component.
But this is only at high magnetic.
Yes.
Low,
Low magnetic field, I have not included the plots here, but they work very similarly. There is not like a specific pattern or whatever, because there is not a pattern in the signal either. So I don't know if there is like a relation between what you see in the signal and what the parameters are, because it gets more messy. So I don't know if you can like mathematically obtain a connection between this.
I can imagine like the relation between the signal and the A set, but the A perpendicular is more depends more on the times you apply the sequence, but not in tau. It also depends in tau.
I see.
Do you think that your model, I mean, you use your neural network to predict two constant, to apply it two-dimensional, but do you think that it would be scalable to models where you have more coupling constants?
So 3 dimensions or well, that was the idea that we had in mind, but like the biggest difficulty in this case was the computation, because you go from I mean maybe 10,000 parameters to 100,000 parameters that you have to train, that you have to, so it gets more complicated in this sense. But in principle, I don't see why it would not work, apart from this.
Conceptually, the same story.
Yes, I mean, concept is the same, but
You can put many dimensions, but probably the
scales a lot in
scales
computation.
very well, but then maybe you can join with Monte Carlo, which is that
Yes,
it's an endpoint set and very function.
Yes.
That's in some ways similar to doing the
Yes.
It's here and on axis and we do more stable. However, maybe you connect with Monte Carlo techniques that essentially design for that kind of things, but maybe you can scale in some way.
Yes, you can find this same structure for 3 dimensions. It's like implemented in PyTorch and everything, so that's no problem. I know about 4 dimensions, 5, etc., but up to 3, I think it's feasible.
But for parameters to go some, let's say, random stuff. Otherwise, that connection with scale.
Yes, but we have not tried, so I can't say this.
Because people are really interested in like you characterize how many qubits, maybe with this, like the coupling that you have like chip with qubits, and you want to know the coupling with this one and this one, but the scale is value.
Yes, I think that the problem is that this has some limits, because I don't know if for 4 or 5 parameters it would not be effective, would not be like knowledge plan.
No.
I also got a question related with this. So, where do you think there is the problem of the decreasing performance when you increase the number of MB? So, is the neural network or the post-processing part?
With many spins, you mean with? I think that the network and the processing part, like, kind of make a whole model. They cannot be thought as independent things, because like you adjust the post-processing to your network and goes like in a pack. But I suppose that if you have more nuclei in your signal, you have to like guess the signal with more accuracy in order to obtain all the information.
Because I would think that if you have many spins, the clusters will be closer together, and then differentiating 2 clusters with the nearest neighbor clustering method, I guess it's...
Well, that's one of the problems. In cases that you have 2 very close, that there are some limits, of course, in your image. There are some limits in how close they are. But also I think that the identification per se is more complicated. You have many more parameters.
Have you thought about using something like the Basque? Like because the nearest neighbor has this problem that if you have 2 clustered together but only connected with 1 pixel, you classify both as the same. because there is no way of cutting. And techniques like the Basque allows you to differentiate clusters that are closer, but they have like a valley between them.
I don't know about the name that you said, but we have used something similar in, well, I think that it's the same but from another name, or I don't know. But yes, in cases that you identify one region of pixels and you have two maximum values, you can also differentiate them. But the problem is that this also has a limit. Well, you can establish this limit like in your program. In our case, it is about 3 kilohertz, like the minimum distance that you can differentiate, and this, of course, it's part of the network of how well it predicts this distinction, and part of the process of the image post-process that you apply after, if it's capable of separating these two weights. But that's like a complicated point, or yes, a tricky point. I don't know.
So, which is your complicated technique? The technique which is what? The technique which is close to this one, the one of the Korean paper, probably.
Yes.
Why do you believe yours is better?
Well, it is similar in the sense that it is a neural network and all of that, but the model was based on taking each of these resonances and extract from each one of them if there are 0, 1, 2 spins in there. So, like, the approach is quite different because, of course, you cannot do something like this in this case. Well, the approach was kind of tailored to their experiment because they have an experimental setup and they wanted something that worked for them, for their signals. So it's something like specific to their problem. And that's it. Then, well, I mean, some things are comparable, other things are more difficult to compare because, well, there are like many things that you can compare, but I don't know if it's possible to make a fair comparison of both.
Because can you make that to make the things faster? Probably what is the high regime essentially it will not analyze the part which are close to one, right? And we just focus on the peaks, right? To make the things faster. But then this starts to approach to the other, let's say, with Korean, where they are only. No?
Yes.
But yeah, maybe.
Yes, for example, one thing that we have thought recently was this thing that I mentioned here. For example, here it would be quite useful to have this image representation because even if you cannot predict the exact values of the coupling parameters, you can obtain maybe like a blurred image or some idea or where the spins would be. And for example, other techniques cannot do this, I think. But well, this image representation can be useful in other scenarios. I really like this idea, that's why I included it here. But it's just an idea as well, if it will work or not. Yes.
Have you thought of using Fisher information to determine the ultimate or estimating these?
Well, I have thought, but I have not done anything. So I haven't done anything similar to this. So maybe it could be done, but I don't know. The only thing that we thought about was like optimizing, but not like something similar to this, an optimization of the experiment itself, like seeing what are the results and But I mean, the high field case there is not a big problem. There was a little bit of problem in the low field regime because we saw that when there are many spins, I cannot show you because I don't have here the plots, but there happens some kind of compensation, and the plots that you see start to look like this. They look like this when you have many spins. So this means that in this region you are getting no information at all because this pattern repeats in all the samples. So you are losing all this information from the signal, and well, this maybe gives the sequence to the number of passes, etc. So yes, but this only happens as far as we are aware in the low field regime. So that is one point that could be improved also. But well, many things to do. Well, the idea in this paper was first of all to present the model as an architecture, as a model that can be used, and then this is more like the physical part of the problem, which of course can be improved in many ways. But that's it.
Is there an equation on why applying this past sequence you can extract a constant? Because you can extract a constant, the coupling constant between these things. I mean, you say you apply pi patches, separate somehow.
Yes, because when the resonance frequency of the coupling is equal to the frequency of the sequence, you see this resonance things. So changing this tau makes the frequency change, and so you could represent this as in terms of the frequency, it's the same.
Yeah, but when the past sequence, the x-axis is time, evolution time, or it's just
It's time. It's the time here. This tau
it is the tau, the separation.
is the separation, but in time between half the separation between the pulses. So you make the sequence longer and longer for each point. Is that clear?
I mean, yeah, I don't know, I don't see what maybe it's.
Yes, it's quite common to use this. Ya está.